today we're going to discuss the last section of this unit, and we're going to talk about oxidation-reduction reactions. So first of all, oxidation-reduction reactions are reactions where electrons are transferred, and they're also called redox reactions. Most energy production reactions are of this type, and they don't have to be ionic compounds, they can be other things as well. So let's talk about the oxidation part of a redox reaction. Oxidation states are also called oxidation numbers, and we need to find those out for every compound before we can move on with balancing this type of reaction. And basically what this does is helps keep track of the electrons as they're transferred, because that's what a redox reaction is. These are kind of like the charges on ions, but we write them a little bit differently, and sometimes they aren't the same. In covalent compounds, electrons get assigned to the atom that has more pull on them. So if you remember, like partially positive, things like that, that's kind of what we're talking about there. The sum of the oxidation states must equal 0, or if it's an ion, it must equal the overall charge of the ion. So for ions, we always write our charge as the number and then the sign. So if something is a 2+ charge, we would put the 2 and then the plus. So the sign always goes after the number. For oxidation states, the sign goes before the number. So if it has an oxidation state of +2, we put the sign first. Okay, a couple of rules for determining oxidation states for particular elements in a compound. If it's the element by itself, so it's in its neutral state, then the oxidation state is 0. If it's a monatomic ion, so if something is aqueous, it's the charge on the ion, and that's what you're going to run into most often. Fluorine always has an oxidation state of a -1. Oxygen always has an oxidation state of a -2. And hydrogen always has an oxidation state of a +1. So usually you can use those to figure out the oxidation states of whatever else is bonded in the compound. So let's look at an example. So assign oxidation states to these atoms. So we don't know the oxidation state for carbon, but we do know that for oxygen, the state is always -2. And so if this is -2 and we want overall for it to be neutral, that means that carbon must be a +4 oxidation state. So in this case, it is similar to the charges. Okay, let's look at SF6. Well, I don't know the oxidation state of sulfur, but I do know that for fluorine, it's always a -1. So that makes this total a -6. If I want the total to equal 0, sulfur has to be a +6. Okay, now let's look at one where we have an overall charge on the ion. Well, I know that oxygen is still a -2 oxidation state. That gives this a -6, but instead of it adding up to 0 this time, I wanted to add up to -1. So that means that nitrogen must be a +5 oxidation state in order for that to occur. Okay, now let's talk about the two parts. So oxidation is an increase in oxidation state. So what that means is that it's lost electrons. So its oxidation state could go from +2 to +3 because it lost some electrons. Okay, so let's look at this reaction. Sodium is the part of this reaction that is oxidized because initially in its overall elemental state, its oxidation state is 0. So as a reactant, it has an oxidation state of 0. But then if we look at it as the product, here we know that this is going to break apart into its ions. So now we have monatomic ions. Oxidation state equals the charge. And so here our chlorine's -1, making sodium a +1 oxidation state. So it lost electrons. It went from 0 to +1, so it was oxidized. We would also say that sodium is what's called the reducing agent because it was an electron donor. So it gave up electrons, its oxidation number increased. Now let's look at the opposite part, which is reduction. This is a decrease in oxidation state, so it's going to gain electrons. So if we look at our same example, let's look at chlorine. Chlorine in this case is the part that is reduced because initially it has an oxidation state of 0, it's in its neutral elemental state, and then like we talked about before, because the oxidation state on sodium is a +1, the oxidation state on chlorine has to be a -1. And so here it's what's called the oxidizing agent because it's an electron acceptor. So it gained electrons and its oxidation number was reduced. So that's how I remember reduction oxidation. If the oxidation number was reduced, I know that then it was reduced, making it the oxidizing agent, and then the other one, is the opposite. So however you can remember that. So let's look at an example. So identify the atoms that are oxidized and reduced, and specify oxidizing and reducing agents. Well, right away I see oxygen by itself, so I know that it's a 0. Here I've got lead and sulfur. I know that the monatomic, if sulfur was a monatomic ion, its charge would be a 2-, so I'm going to say that sulfur has a -2 oxidation state, making lead a +2 oxidation state on the reactant side. Now if we go to the product side, I know oxygen is always going to have a -2 oxidation state when it's not by itself. This makes lead a +2 oxidation state. We look at our SO2 again. Oxygen is a -2. There's 2 of them. That makes a total of a -4, giving sulfur a +4. And so here, lead is actually not changing at all, so we're not going to include it. Sulfur goes from a -2 to a +4. So this means that it was oxidized because it lost electrons, making it the reducing agent. Now, oxygen went from a 0 to a -2, so it was reduced, making it the oxidizing agent.